know, we are done with linear shift invariant systems.
Oh, we're never done with them.
You're not really done, but
We live them on.
they really come up again in the course. I mean, we could bring them back, but we don't normally. Actually, you know what? I'm slightly wrong on that. They'll show up again when we do. We're going to do an example of fitting a neuron, and that's a bunch of weeks away. And when we do that, they'll be kind of in there. Okay. So now we start like the rest of the course. And the rest of the course is basically statistics. But the way we do it here is a little different than, probably a lot of you have had a statistics course of some sort or other. And in that course, you probably learned about computing basically like means and variances and correlation coefficients, and then doing tests like t-tests and measuring whether something is statistically significant. So we will talk about those things, but we're going to try to, as we've done with all of the course, we're going to try to build these things sort of from the ground up and give you a sense of where they came from. And another important comment is that the field of statistics is diverse, it's old, it's diverse, it's pretty complicated, and it's going through a major revolution, really in the last 30 or so years, and that's because of computers. Everything we do in statistics is being kind of redone, and this is a challenge. It's a challenge for teaching it, it's a challenge for doing it and for using it, and you can see both the upside and the downside of that challenge. We read all the time about articles in journals that turn out to have done things that are not correct, or they claim things that are statistically significant when they're not. Sometimes that's because people are using procedures or canned software in the wrong way, or more often it's more about sort of subtleties about how they interpret the outcome of statistical procedures. So we're not going to be able to fix all of that in the remaining weeks that we have in this course, but we will try to give you a sort of blend, which is a little bit of the sort of historical view of statistics, which goes back a couple hundred years, and a little bit of, and probably a little bit more than a little bit, of a sort of modern perspective on how to deal with statistics in the era of, let's call it the era of data. Right? So nowadays, we do everything with computer programs. We do calculations that couldn't be done 50 years ago. And so statistics has evolved slowly. It's a rather conservative field, I guess I would say. The part of the field that races ahead is more sort of machine learning. I'll say a little bit more about the history. I think I have a slide in here. So let me just jump right ahead to the slides. Okay. So what we're going to do is we're going to talk about, it's really broken into two sections. We're going to start with some basics that are about really where did statistics come from? It comes from summarizing data. So we'll talk about that today. And we'll talk about probability, because you can't really talk about statistics without thinking a little bit about probability, because implicitly, when we do calculations on data, we're always imagining, whether we admit it or not, we're imagining some sort of model where the data came from or drawn from some sort of probability distribution. So we'll talk about probability just to make sure everybody's up to speed on how we think about that. And then we'll do a section after this. There's really two more sections of the course, although they're both about statistics. So this one is called Summary Statistics and Probability, and then we'll follow this with what we would call statistical inference. How do we actually extract or infer things from data? How do we test whether we believe those things? How do we compare things that we get, let's say, from different data sets or across different experiments? And a lot of this, just to be clear, is sort of the core of all of science. So most of you are not aiming to be theorists or computational psychologists or computational neuroscientists. That's fine. You're still going to have to use these things, and you're going to face them every day. And you already know this. Every time you read a paper, you're reading about statistical analyses and statistical claims of significance, et cetera, et cetera. Okay. So here's a quote from Efron and Tibshirani. These are two faculty at Stanford that wrote a great book that we'll refer to at some point on bootstrapping. And here's their description of statistics. Ooh, let's ended up with a kind of crummy. I got a new copy of this, and it's still crummy. All right. Well, hopefully it looks okay for you guys, and you can read it. I think this is a cool quote about what statistics is, because you probably think of statistics as this very dry, somewhat boring thing where you crank out little calculations and look things up in tables and figure out whether your data, whether your hypothesis is significant compared to some null hypothesis. But I like the way they describe it. Statistics is the science of learning from experience. So, I mean, just read that first sentence and the first phrase, and that's like learning from experience. Isn't that what biological organisms do? Isn't that what we're doing right now? Pretty much. So already, even in the first phrase, we see that thinking about statistics broadly is actually, it's got two meanings, and these two meanings run through this course. The one meaning has to do with, just basically figuring out what to do with data, how to do analysis, how to parse your data, how to compute things from it. But there's this other kind of hidden, almost implicit meaning, which is it's about doing what a biological organism does, but formalizing it. So you're receiving data right now. Your eyes, your ears, all of your sensory systems, data are coming in, and you are processing them, and you are analyzing them, and you are inferring things about the world from those data. So really a biological organism is doing some sort of, in some abstract sense, is doing statistics, is doing calculations that are statistical, because the measurements you're making are partial and they're noisy. And so your brain is sort of a statistical calculating engine, whether you realize it or not. And it was when you were born, even though you didn't know what statistics were, your brain did, and knows how to deal with the statistical nature of the world, the fact that your observations are partial and noisy. Okay, so statistics is the science of learning from experience, especially experience that arrives a little bit at a time, so even more biological. Earliest information science was statistics. It originated in around 1650. So people started talking about doing these kinds of calculations in the 1600s. So it's really old. It's really, in a sense, it began when we started thinking about science, about making measurements, and about inferring things about the world from those measurements. So this century, and they're referring to the last century, because this was written in the late 1900s, this century has seen statistical techniques become analytic methods of choice in biomedical science, psychology, education, economics, communication theory, sociology, genetic studies, epidemiology, and other areas. They didn't mention neuroscience, which is a shame. But obviously, you should include physics there, you should put chemistry there, basically all scientific endeavors, and really all social sciences. We've got economics in there, sociology. Traditional sciences like geology, physics, and astronomy have begun to make increasing use of statistical methods. So if you now talk to people in physics about what they do, you find out that 90% of it, if they're dealing with data, they're dealing with statistics. Okay. People are not natural-born statisticians, so I don't agree with that. But what they mean is we're not born knowing how to do statistics calculations like to do math. Left to our own devices, we're not good at picking out patterns from a sea of noisy data. We are too good, this is actually the right way to say it, I think. We are too good at picking out non-existent patterns that happen to suit our purposes. So this is so your brain is a statistical engine. When you're born, you learn how to see, largely. You figure out what are the patterns that are interesting, what are the patterns that allow you to learn things about the world, what are the patterns that allow you to make predictions about what the world will do. And in learning how to do that, your brain builds up a sort of understanding of how the world behaves. And your brain wants to interpret everything you see in terms of those expectations, those sort of things that it's come to understand about the world. So when you look at the clouds and you think you see a face, there's not really a face there, but your brain is basically taking whatever pattern of stuff is up there in the moisture in the air and sort of saying, well, it looks a little face-like, so it jumps to a conclusion that it's a face because it's used to seeing faces. We're social creatures. We look at faces all the time, so you have a preference for, almost a bias towards seeing things that look like faces as faces. So that's we're too good at picking out non-existent patterns. So when you look at data, your brain is doing that too. When you look at a scatter plot of points, you're probably imagining all kinds of things. So we have these tendencies or biases to see things that are based on stuff we've seen before. Anyway, the point is, if you're trying to do science and you're trying to be objective about it, you're not supposed to let your built-in visual biases or auditory biases or any other biases enter into the process. You're supposed to be being as objective as possible, and you want to be able to produce things that can be replicated, they can be communicated to other scientists, and that are going to become part of the fabric of our scientific understanding. So we try to push back on our own implicit and internal biases, and we try to structure this in a formal way so that we can be precise about what we're saying and as objective as possible. You find out when you kind of dig into this that there's no such thing as objective, that all measurements and all interpretations of measurements are going to require you to make some assumptions somehow, and those assumptions are going to be imposing biases. And I think the right statement for science is not that you shouldn't have biases or assumptions because you have to. The statement should be that you should explicitly state those. That is, rather than keep them hidden and do something that is an interpretation that you stuck in there, you should state up front. This is a very mathematician kind of view, right? You state your assumptions up front. Here's what I'm going to assume, and then, if we assume those things, then we can do this calculation, and this is how it comes out. Okay. Statistical theory attacks this problem for both ends. It provides methods for finding real signal in a noisy background. So a lot of statistics is about taking noisy measurements and trying to clean them up, get rid of the noise, average over it. We'll talk about that in just a moment. But it also provides strict checks against overinterpretation. So we're going to have formal methods for sort of verifying and testing things and checking whether we're reading too much into the data. And that's something that we can actually do in our personal experience, and you do it all the time. When you think you see that face in the clouds, you study it a little more carefully, and then you realize that's not a face at all because the cloud just moved a little bit, and now it looks nothing like a face. Now it looks like a, I don't know, like a scorpion. Now it looks like a frying pan. Now it looks like something, right? So it's changing, and you realize there's no face there. I was just hallucinating something. So we have, and that's maybe a silly example, but you know the truth is that all the time you're faced with ambiguous sensory experiences, things that you cannot determine explicitly or with confidence. And what do? You gather more information, you look more carefully, or you shine a light. You're in a dim room, you can't quite see what's in the back, and you think it might be a mouse back there. So you turn on the lights and find out it's not a mouse, there was just an eraser sitting on the floor. So you gather more in, just like in science. If you're not sure about something, you gather more data, you find a different way to observe it, you make different kinds of measurements until you can be a little bit more sure, and then you can state what the result is. So I sort of disagree with that we're not natural-born statisticians. In some sense, we are. We do these things. Science is just a formalization of what we do all day, every day since we're born. We learn from data. We figure out how to organize things and structure things so that we can interpret them in a kind of rational and coherent way. And we do that throughout our entire lives. And science is, of course, a community-wide endeavor where we try to do that as a species. Right? We try to share this information, and we have checks and balances to make sure that the information that we're putting into that pool fits with the other information and is consistent. So it's not just about your own internal mindset, it's about how does it fit with everybody else. It becomes sort of cultural. Okay. So that's, I like that quote. So here's a little bit of the history. I sort of started to mention this. So in the 1600s, people start thinking about averaging data, summarizing. Why are they doing that? Well, I think, if I remember, that the initial impetus for this comes from trade. So, you know, I want to trade you 2 sheep for 1 ox. Maybe it's 3 sheep for 1 ox. Actually, an ox is pretty heavy. It's probably like 10 sheep for an ox. Anyway, I've lost track of the correct exchange rate there. But if I lived in the 1600s, I would probably know. When they had to do this, you know, it suddenly became of interest to make sure things were fair. So they wanted to weigh the animals or weigh the group if they were doing grain for sheep or whatever. So they had to weigh things. And they started finding out, well, if you weigh something and then you have a disagreement, you go back and weigh it again, the answer comes out differently. And each time you weigh things, the answer comes out a little bit differently. So then arises the puzzle. Well, what do I do if I make 3 or 4 measurements of something, or if 4 people make the measurement? 4 different people weigh the same ox, and they get 4 different answers. And now what do I do? And initially, the thought was, well, of course, you just pick the best one. You pick the one you like. Sounds familiar for modern data scandals, right? Pick the one you like. Don't tell anybody about the other ones. Just put the good one out there. Hide the other ones. That never happened. And then you're good. But the surprising thing is that they come to a realization that actually they could do better. And you have to decide what you mean by better. But you can do better if you average them. The average is a better description of the true value than any of those measurements. And that is really a revolutionary idea. Because when you first confront it, it's like, well, why should I throw away these actual measurements? This is what I actually measured. Here's the number. Why would I throw those away and replace them with this thing, this average thing? That nobody measured that. We're making it up. It seems like a sort of a crazy idea, and you kind of ask yourselves, you've been doing this for a long time. You probably learned about this in grade school. You read it in the newspaper every day, the average of this, the mean of that. We do it all the time. Why? Why would we do that? It sounds like it's a mistake. Isn't it better to just stick with one of the ones you've got? Find some way to pick one of the ones you've got. Well, there are ways to do that, and I'm sure you guys know about that. But why? Kind of ask yourself why? Why do we do that? All right, we'll come to it. In the 1700s, a reverend, a minister of the church, Thomas Bayes, comes up with this realization that there's a way to describe the process of, he works off of Laplace's ideas and others in working on describing probability in a formal way. And he says, well, the right way to think about measurements is that they're conditional probabilities. They're drawn from some conditional probability. And what you really want to do is flip that around and do the conditional probability in the other way. So he kind of works through the math and writes down a way to think about that, and he calls it inverse probability. And we have him to his label that we use to describe the basic formula that allows us to flip conditional probabilities. We're going to get to this shortly, not today. And we call that Bayes' rule. And so the 1700s emerges this idea that that you can of statistical inference, basically. So this is a big step. So the first step here is just about summarizing data. I have a bunch of measurements and I want to summarize them. So I need to do something like take the mean. The next step is really to do something more. It's really to sort of formalize the idea of extracting information from data, not just to summarize it, but maybe to learn something about hidden elements or to relate things that are hidden from you. And so this really is an important step forward toward thinking about statistics in the context of science, not just to summarize data, but to learn something about the world. I'm jumping forward and skipping over lots of history. In the 1900s, this really starts to get formalized in terms of science, and people like Fisher and others get together and say, well, here's the right way to quantify. If we want to build a large-scale endeavor for doing science and for making measurements, here's how we should think about presenting our results. We should present, when we have distributions of results, we should fit models to those, and we should do that by referring to this thing, by making certain kinds of measurements and certain kinds of calculations. So Fisher champions these ideas. And kind of interestingly, they're a little bit against what Bayes proposed. So there's a schism in the field. And we get this partition into what are often called the Frequentists and the Bayesians. These days, I think because of machine learning, we kind of, that's a sort of confusing and very complicated debate. It's actually quite rich and interesting to think about. And in the end, a lot of it is about, I actually think there really isn't a debate in the end. And yet some people feel very strongly about this and are still fighting about it. It's really sort of almost bizarre to read some of the old literature where people fight about this. It's about whether you should be including any kind of assumptions or biases when you do analysis of data. And Fisher was of the belief that you shouldn't incorporate anything other than using the data itself and the most basic description of where the data come from. And the Bayesians, if you like, said, well, you actually can't do that, and you're fooling yourself if you think you can, because you're actually making assumptions. You're just not admitting them. And they said you should just put everything out in the open and state what your assumptions are. And this went back and forth, and it sort of still goes back and forth. But like I said, some combination of modern engineering and modern machine learning kind of swept a lot of this under the rug. Because the truth is that you want to use both of these sets of ideas, and you want to be careful if you're being Bayesian about the kinds of assumptions you're incorporating, and you don't want to incorporate too many. Okay, so we'll talk. We're going to blend these things together in what we describe for you, and we're not going to fuss too much about who's right or who's wrong, because it sort of doesn't. It ends up becoming, in the end, if you keep pushing on it, it just becomes philosophical, or it becomes sort of nonsense. Like, in the end, they're the same, because they're just kind of relabeling things and hiding and shuffling things around. Okay. In the 1940s, so this frequentist thing is really for science. So Fisher he's very forceful about his views, and he says this is the way you should do science, this is how you should report the results, you should report significance in the following way, testing the null hypothesis, testing against the null hypothesis, et cetera, et cetera. So a lot of those ideas came from Fisher in the 1920s, and they're built into a lot of the ways still that we do science. When you read a standard statistics book that's meant for scientists collecting data, this is really what you read. You read this perspective primarily. Unless you read a more modern textbook, like the one that I think this Hasty's on that. Who did there's a really nice probability book for undergraduates. It's very complete and it's quite beautifully written. I think it's not Hasty and Tim Sharani, but anyway, I'll look it up. I think it's on the web page.
Isn't it the Berkeley book?
Maybe. Anyway, doesn't matter. I'm spacing on who the authors are, but it's actually, I think it's on the web page of the course. Okay. In the 1940s, things kind of flip around again, because now, all of a sudden, we're actually trying to build devices. So the reason this is in the 1940s is because World War II caused the development, and I think I've mentioned this to you before, in linear shift invariant systems, there was a huge burst, a huge growth, and also in statistics. So there was a sudden need to do things like radar tracking, and to figure out how to build missile guidance systems. And basically, it's kind of harsh, but it's about war. It's about weapons and defense. So there's an enormous effort put into building devices that can do things, that can solve real-world problems, like detect things, or measure velocities of things, or decide whether this is this or this. And those problems all involve measurements. The measurements are always noisy, and they involve statistics. So this stuff becomes quite formalized and actually gets embedded into devices, into algorithms, into machines. And this, we kind of call this statistical signal processing or statistical signal analysis and communication. At the same time, things are happening in Bell Labs, like we're figuring out basically how to encode things in digital streams of data. So Shannon, who invented information theory, describes what it takes to compress things and send them out as streams of bits. And so there again, the issue of statistics comes up, and the idea of measuring probabilities of occurrence of things in the world. And the reason that things are compressible is because the probabilities are not uniform. Some things are more frequently occurring than others. And so if you want to represent them efficiently, you can find ways to take advantage or exploit the fact that some things are very prevalent and some things are very infrequent. So the ideas of statistics and using statistics both to eliminate noise, to make decisions, to act on data, or to store data efficiently, to transmit data efficiently, all of those things start happening in the 1940s. And in a sense, these things are, nobody is really saying it, but these things are kind of pushing back a little bit on Fisher. And I think what happened is it was just viewed as a very different use of statistics. It's the same math. You're writing out the same forms in terms of probability, but it's used very differently. So now, you have a device that's trying to detect whether there's an airplane on the radar, and what it's doing is not really what Fisher described. It's taking into account some things about airplanes, some knowledge about airplanes, some knowledge about the statistics of different kinds of airplanes, and the probability of occurrence of an airplane or not an airplane. And so it's taking into account a whole bunch of information that's more than just what's in the data, the measurements, which is what Fisher was pushing for. So already we have this schism starting to build, right? So Fisher's still saying this is the way to do science, and we have all these engineers and signal processing people and statisticians that are working on actually building devices and doing communications, and they're saying, well, actually you have to include this other stuff. And they're building the devices, and the devices work. Okay. In the 1950s, there's a whole bunch of statisticians, Jeffries, Wald, James, Savage, who come back and say, well, actually, you've got to put the Bayesian stuff back in, but there's a lot of pushback, and this stuff is so entrenched, this frequentist view, that it remains to the day, even till now. If you buy a textbook on statistics, it usually has this as the primary view. So it's a very strange configuration that we're in. The modern era is that on top of all of that, which is already a bit complicated and mixed, kind of diverse, if you could call it, if you want to be positive about it instead of complicated, sounds bad, so let's call it rich. It's interesting, it's diverse, and it's pretty confusing at times. Okay. In the 1970s comes computers. And people like Tukey, who was a kind of a computer scientist and kind of a statistician, by the way, Tukey is the person who invented the fast Fourier transform. But he also had all kinds of ideas about how to do computation on data. He was very interested, he was not just interested in writing programs to solve if-then, and write conditional statements and loops. He was really interested in using computers to solve problems using real-world data. And so he was grappling with the statistics issues as well as the programming issues, the efficiency issues. FFT is an efficient algorithm for computing a Fourier transform. So he looked at problems in optimization. He advocated the use of simulation. So this was really important and is an extremely important part of modern statistics. That you don't have to just work off of theory and writing out the math. A lot of times when you're not sure of things, what you do is you build a simulation. You draw samples randomly. You get the computer to draw samples for you. Pretend to draw samples. It doesn't really. You draw samples, pseudo-random samples, and you simulate what would happen if you were to measure something under some conditions. And then you can look at distributions and ask yourself, well, how would I learn about the properties of this distribution based on the samples? So we can actually now simulate the process of measurement using a computer and then work backwards and ask, okay, given that this is what the measurements look like, now I can work backwards and ask, can I come up with a procedure that goes from the measurements back to the source? And that's really what the inference problem is about. So Tukey becomes an advocate for doing that. He introduces algorithms for doing things like that. It's not just Tukey, it's many. Each of these lines has hundreds, if not thousands, of names associated with it. I'm putting a few big ones that are the ones that get associated, most identified with some of these ideas. Okay. In the 1990s, things really start to take off. So Tukey had a vision that computers were going to play a big role in statistics, and they were going to change the way we solved these problems. And he was right, but he was prescient about it. So he said this in the early 1970s, and it wasn't really, people were doing things all along, but they weren't that successful because computers were too wimpy, and because the methods and the way of thinking was a little bit too simplistic. But slowly and surely, machine learning emerges, I would say in the 90s, and computers get powerful enough that we can now start processing lots of data. And to you guys, this probably sounds silly that I'm standing here saying this, because it seems like it's always been like it is today, where Google has 100 billion images, maybe it's 1 trillion images, I don't even know, in their online databases, and they have and Facebook has God knows how many accounts and information about all of us. I mean, the amount of data is just absolutely staggering. And the kinds of computation that need to be done, as I'm sure all of you are aware, now require enormous amounts of power. They get situated in huge data centers that are usually next to major rivers where they divert the river to cool all of that equipment because it's throwing off tons of waste heat. And the whole world has changed in the last, not really like 10, 15 years. But it started in the 90s, I would say. It started back here in the 1940s. This is really the beginning of this, because we're trying to build devices and machines and to do calculations that are on data. So it's here, Tukey's vision starts to emerge as, wow, we're going to really do learning. We're going to learn from data. Just like that quote about statistics being the science of learning. Now we're really going to do learning from real data. We're going to build machines that can learn maybe even a bit like people learn. And we're going to do that off of data. We're going to do it off of huge amounts of data and huge amounts of computing. So the ideas of statistics are all still in there. We're just doing a lot of it with simulation and with powerful computations rather than writing out the math and saying, if you have this kind of distribution, you can do this calculation. Okay. And just a little side note. And that's where we are now. And I mean, you all know that. To me, it's shocking. Right? This is really, because Mike and I both, but I got my degree in '93, my PhD. So we had computers. We weren't writing on paper. We had computers and we had email. There was an internet. You could copy files back and forth. So it wasn't. There were no dinosaurs on the earth. So it was still, it was sort of modern. But still, it's really stunning. It's shocking. There were no cell phones, although it was soon after that cell phones emerged, late 90s. And that just amplified everything. So the use and need for data and communications, that, again, these ideas started here. Shannon, communication theory, how do you send digital data over a transmission line? We're still using that, right? So these fundamentals are still with us and are allowing this to happen. So you have to go back, about 70 years to sort of see where these things came from. And really further, if you want to go back to the 1600s, people weighing oxen and sheep, you can go all the way back to that. Okay. One other little side point, since you guys are sort of psychology and neuroscience oriented, this is kind of cool too. Starting in around the 1950s, some of these people, especially James, it turns out, he's a physicist, statistical physicist. But he starts to recognize that you can actually think about the functions of the brain, of any brain, as doing statistics, calculating statistics on inputs. And I said that a few minutes ago because, well, that's kind of what I work on, and it's sort of what Mike works on, and a lot of people in the field now think of it that way. Maybe it's even becoming almost a standard view. But back then, it was not so standard. And for evidence of that, you can actually search on the web and find. James tried to submit papers describing this, and they were rejected. And he became very bitter. He wrote these scathing responses to the editor, some of which you can find online. They're actually quite amusing. I shouldn't laugh at somebody's misfortune, but he got very angry, which was understandable because he had really brilliant ideas, but they weren't very testable. Right? It was kind of early stages. He was saying this in the 1950s. He actually wrote these things all the way through the 1990s, and he wrote an absolutely spectacular textbook called The Logic of Science,
Yeah.
Probability, The Logic of Science, I think it's called. Yeah, and it's really wonderful, and that's also online. You can buy a hard copy, but it's online. So James basically said, you can explain the brain as doing statistical calculations, and maybe you can explain learning and what we do, starting as infants, as a process of statistical, sort of meta-statistical calculations, like building up probabilistic descriptions of the world and then using them to interpret data. And I think that view has a lot of merit. It's not the only way to think about it, but it has a lot of merit, and you can see very beautiful examples of where that plays out. Okay. Enough. Mike is sitting here amused because I always babble at the beginning of this, and he always says, I don't know how you do that.
Just because I'm incapable.
It just comes naturally to me. I don't know how I do anything else. All right. So out of a lot of this, when you bring this back to science, sort of take it away from engineering and machine learning and how do we make devices and how do we build computer systems to do these things. You can come back to science and you say, so what does that mean for us? Now, all this stuff has happened, and in some sense, statistical inference and machine learning have been just a gigantic success. It's hard to argue against that. You can argue that there are negative sides to that success. There are dangers, there are concerns, there are mistakes being made. You can argue all of those things, but you can't argue that it's not, in a sense, a success, because it has just swept the planet. So I guess you could argue that's not. Let's not. Okay, back to science, because we're going to think about science. So how does this play out in science? Well, you observe some, this is kind of a cycle. You can find examples of diagrams like this all over the place. Many textbooks describe things like this. This is just my version. You observe or you measure data. Then you have to summarize that data maybe by just computing things like the mean, or maybe by fitting models to the data. To sort of provide some structure, to say the data seem to be described in the following way, and I'm going to fit some curve, or I'm going to fit some plane, or I'm going to fit some hyperplane, or I'm going to fit some sort of ellipse or ellipsoid, all those things we've talked about in linear algebra and least squares. Those are all going to come back. We're going to revisit and reuse a lot of those things. And then, depending on how that comes out, maybe I'm going to compare several models, or I'm going to take a model, once I've fit it to the data, I'm going to make some predictions and test how well those come out. And depending on how that comes out, I might say, wow, it works really well, or I might say, gee, it's working really well here, but it's failing over here. Or here's a new measurement that my colleague in another university just made, and I can't explain that at all. It doesn't fit with my model. So now we're going to modify, or either create or modify the model. We can call that a hypothesis, or we can call it a model. If it's precisely described, we usually would call it a model, something that we can write down, maybe with math. And then we're going to go back and generate some new predictions, design a new experiment, and make some more measurements. And so this cycle of kind of going around of making measurements and then modifying models, making measurements, modifying models, and connecting them with these side lobes is the process of science. And it's not, we're never done. We're never going to have the model or the answer. All models are wrong. We talked about that in the beginning. What we're going to do is we're just going to keep doing this. Sisyphus. It never ends. Until the heat death of the planet, we will be doing this. I'm so cheery this morning. I'm so happy to be spreading that. Oops, we already did that. Okay. All right, so back to this thing. So here's Fisher. And Fisher says, I think this is a quote from him, I'm pretty sure. They didn't put quotation marks around. You get a bunch of measurements, and Fisher says to us, well, the purpose of statistics, the whole point of it, is to replace all these numbers with a small number of quantities that contain as much as possible of the whole, ideally the whole, of the relevant information contained in the original data. So I think that concept is a very sound one. So here's a bunch of numbers. If I want to communicate, and this now becomes, it's like what Shannon told us, right? It's kind of about communicating. I want to communicate to you, to the world. I want to write in a scientific publication what I've discovered. I don't want to give you a long list of numbers. Here's what I discovered. Here's 10,000 measurements that I made. I'll just put them in the appendix. These days you can put anything you want in the appendix. The supplementary materials. You put them online, you just put the numbers there, and you say, and your paper is one paragraph long, see supplementary materials. Okay. We don't do that. Because looking at those numbers is kind of useless. The whole point is to interpret those numbers and to learn something from them. What do we get out of that? And so what Fisher is trying to say is that the process of statistics is trying to summarize these with maybe a small number of numbers, a small set of values that capture what's important here. And, so he's sort of, because it's, 1920s, 1930s, a lot of these things are just scalars, as they are here on the board. And of course, we're going to think about things as vectors, and we're going to think about more complicated things. But if you start with scalars, this is just about saying, well, I have a bunch of measurements, and I need to summarize them. And I think the only thing that's missing from Fisher from this statement is he says relevant information. And who's going to decide what's relevant? So he's trying to say something quantitative. And in fact, everything he says about this is quantitative, describing and summarizing these numbers. Except this word relevant is suddenly not very quantitative. It's not very objective. It's kind of subjective. Who says it's relevant? Relevant for what? Relevant to who? Relevant under what conditions? So the problem becomes, defining what we mean by relevant. If you have a bunch of measurements and they are scalars, so we can plot them along some line, let's call this x, and we make a bunch of measurements and they fall in various places, and we know that if we have a few of them, we might just give the list like that. If we have a lot of them, we have 10,000 of them, one way we would summarize them graphically is we would build something like a histogram. So you bin these and you count how many fall in each bin. So here's the first bin, it has 3. And here's the next bin, it has 4. And here's the next bin, it only has 1. Here's the next bin, it has 2. And that becomes a summary. So now instead of sending you I only have 10 numbers here, but there were 10,000. The point is that I only now am going to express this with 1, 2, 3, 4 numbers. I have to give you these 4 numbers. Actually, I have to give you 8, right? Because each bin has a center position that has a height. And I have to give you all the center positions at all the heights, and then I say, oh, wait a second, they're equally spaced, so I don't need to give you all those center positions. I can just give you the first one and tell you the gap between them. So actually, I need maybe 6 numbers to describe this. And if there were 10,000 data points, and I'm providing you with these 6 numbers, I've just greatly reduced my description, right? So I replace a quantity of data, a large quantity of data, by few quantities. The first bin, the spacing between the bins, and the height of each of the bins. And depending on my bin width, I can do that with a very small number of values compared to the 10,000 data points. All right, so we just succeeded, and maybe we just stop there. But you guys know that a common way of describing data. So here's data. Here's another example. So these are this is histograms. Or you can either think of this as a histogram, or you can think of these as data that only occur at discrete values. And what's meant to be illustrated here is, well, this one occurs once, here's one that occurs here, one that occurs here. This is like double height because I got 2 of these when I was making my measurements, and then one of each of these. Okay, so there's my data. And a totally standard thing to do, which you're all familiar with, whoops, these came out in the wrong order, is to think about using, instead of a histogram, providing 2 numbers. So not 6 numbers, as I was describing on the board, 2 numbers. What are the 2 numbers? Well, if we want to be general about it, we would say one of them is supposed to capture sort of the central tendency. Like, where's the middle of the data? What's a typical example? What's something that falls right in the middle? And then the other one might capture something like how wide, how dispersed are the data, how spread out are the data around that typical value. So the generic phrases that get used are central tendency, like where's the center of the data, and dispersion, how broadly spread is the data. I'm using these deliberately, these general terms, they're kind of vague, because you guys already probably know what the most standard or most common choices are for these 2 things. What are they? What do I usually present here? The mean, the average if we want. I'll give you some terminology in a second. And what do we usually use here? Yeah, like we measure the variance or the standard deviation. So the most common thing, and the thing we always jump to is let's measure the mean, let's measure the standard deviation. That's the most common thing you see in all statistical literature to summarize data. And those are measures of the central tendency and the dispersion. The word mean, there's some technicalities there. Usually, we're going to call something like this, if I have discrete data and a finite amount of it, then when I calculate we can casually refer to the mean. That's the sum of the data divided by the number of data points, right? We can also typically call that an average, or we can call it the sample mean. It's a mean of a bunch of data samples. I have samples that are drawn from some experiment or from some device, and if we want to be specific about it, and especially when we start talking about probability, we're going to call this the sample mean. It's the average over the data. And we might call this the sample standard deviation. It's computed on the data. Okay. And okay, so how does this work? So let's go back to the sample mean or the average. Why do we use the sample? Why do we use that? Who said we should use that? I'm sure you guys all know that there are other choices. Right? What else can we, if we don't want to use the mean, what can we use? All right, probably the second most common choice is the median. Right? How do you calculate the median of the data on the previous slide? What's the median? So you basically start counting from both ends. The median's like the thing in the middle in terms of the number of data samples. So 1, 2, 3, 4. Okay, I landed here. My fingers met when I got to here, so this is the median right here. It's this one that's double height. It also happens to be the one that's double height. There's another thing. Anybody think of something else we might use? If you have a lot of data, it's really more appropriate when you have a whole distribution. But so there's the mean, sample mean. There's the median. There's the mode. What's the mode?
Value that occurs most often.
Right. So the mode is like the peak if you're making a histogram or a distribution. So the thing that occurs the most frequently. So that the mode here is actually equal to the median. You can already kind of guess that the mean. Where's the mean going to be? You think it'll be here also? Probably not. Yeah. So the mean. Actually, it's kind of the mnemonic is what was on the slide before. If this was a seesaw, and these were weights, and the plank has no weight, so it's just these things have unit mass, whatever it is, the mean is actually the place that balances the seesaw. It's like, where would you have to put that little triangle so that this thing was perfectly balanced? And you can kind of see by eye that that thing is not going to be under these guys. Why not? Because if it was under these guys, these wouldn't count, because they're right at the fulcrum. And the ones to the left and the ones to the right, well, there's 3 to the left and 3 to the right, but the ones to the right are way further out. So this seesaw, if I put the fulcrum here, would drop down very quickly, right? If you have 2 people on a seesaw, when you have kids who learn this, and one of them weighs 40 pounds, and the other one weighs 170 pounds, where do they have to sit in order to actually have a reasonably good time seesawing? The 170-pound person has to sit in close to the fulcrum, right? And the 40-pound person can sit way, way out on the end, and then you're actually pretty balanced. Right? So here we are. So these things, if you want to balance this thing, you're going to have to move the fulcrum to the right, because these things are so far, this one is so far out. Okay, so the mean will be somewhere to the right of the median and the mode. Okay, so that's 3 things that we could use for this central tendency: mean, median, mode. And there are others. There's actually a whole family of them. So let me go back to the question, and then we'll talk about the family. Why do we do the mean? Well, part of it's already on the slide, right? We did all this stuff with least squares. So when you set up an optimization problem, you say, I want to minimize something. Why did we do all that stuff with least squares? Why do we always write the thing that we wanted to minimize as a sum of squares? Who said that was the right thing to do? I mean, all these things fit together, right? This is this long history of people grappling with data, thinking about how to measure things, thinking about how to quantify things, thinking about how to optimize things. And we always come back to this one central set of tools that has to do with sums of squares. And Why is that? You've already seen some reasons why, and we've been working with these things, right? It's one simple answer is just that we can write down the answer. When you write down this problem, so I'm going to minimize, I want argmin, okay? I want to minimize something that I can subtract off from, here's my data points, x sub n. I want to subtract something off from all of them, and I want to square the difference between each of my data points and that thing I've subtracted off. And I'm going to add that up. I'll turn it into an average. That's not going to matter for computing the argmin. This 1 over n isn't going to make any difference. It's just a scale factor. But we'll put it there because we'll include it later. And I want to minimize this over c. What's the answer to this problem? What's the c that minimizes this? Well, let's write out the linear algebra. We know how to do the linear algebra version. We did this for regression, right? Except this is even simpler than regression, just one variable. All right, so this thing, the xn minus c, and the square, and the sum, and we put 1 over n here, right? So and we want argmin of that. And that's argmin of, well, let's write it in vector form. So let's make x be a vector that contains x1, x2. It contains the data. We've done that before many times. It's just a column vector with all the data in it. So, and then this thing, because it's a sum of squares, well, we know what we're going to do with that. How do we get sums of squares when we're working with linear algebra? That's a vector length, right? The sum of the squared elements is the vector length. So if I think of a vector that contains this, then this thing, the sum of the squares, will be the vector length. So all I need to do is write the vector length of what? Well, it's x minus, well, now I have to subtract some number c off of every element of x. And now it's a little bit messy in terms of notation. How do I do that? I have all these elements of x. I want to subtract off of each element the same thing. How do I write it? If I make a vector full of 1s, I could subtract 1 off of every element of x, but I don't want to subtract 1, I want to subtract c. So I just take c times the vector full of 1s. So let's make 1 the vector full of 1s. I take c times that, now I have a vector full of c's. I subtract that from x, now I have a vector full of the elements of x minus c's, all of those elements, and now I take the squared length of that, and that's this. Oh, I left one thing out, which is the 1 over n. Okay. Nothing new here. This is what we did for regression, right? We rewrote the problem instead of writing a summation over, to write this out, little n. We turned it into a vector equation, and then we solved it. Okay, so what's the solution to this? Now it looks like regression. How do I solve for c? Anybody remember what the answer is? Should we just write it down, or should we actually write out how to solve? Anybody going to tell me what the answer is? That would be good. How can we solve this problem? I want to minimize this over c. Three ways. We gave you 3 ways to solve this problem when we did regression. Right? One was calculus, because this is just a scalar problem. So to make the derivative of this thing with respect to c, I can set it equal to 0, and I can solve for that, and that'll give me the answer. So that's like plain old calculus. You knew how to do that before you took this class. And then I had sort of fancier ways. One with SVD. SVD is kind of overkill here. You could do it, but it's a little bit overkill. And then we had this orthogonality principle, and each of those was a way of deriving the answer. But the answer in the end was pretty simple. You know the answer is the mean of x. Well, that's on the slide. Come on, man. I want to know how to write it in linear algebra. I want to write down what's the answer to this problem. And then we'll say that it's the same as that. We'll come back to that. But let's write down the answer. I want to use the things we already learned. We already learned how to solve this regression problem using linear algebra. What's the answer?
X times the pseudo inverse of 1s.
Oops. Yeah. Okay. I guess I better write mu for mean. mean is, let's do it this way and see if this rings a bell. That look familiar? No. Completely drawing a blank. Whoa. It's the dot product of x with 1 and the dot product of 1 with 1. And technically I need a 1 over n in all of these if I'm going to include that and carry
Yeah,
it
the
on.
1 over n you get.
It's going to cancel them. I'm feeling a need to,
No, you don't need anything. It's perfect.
it will cancel.
There is no cancel. You get 1 over n right there. And you don't want it to cancel.
Isn't the denominator already overhead?
I was looking back at in the old slides to see if we can just pop it up. So it's in the notes.
Shall we take a break, perhaps?
We will in a second.
I believe.
We have to finish this. There's an old slide. That's regression. And we were minimizing, so it looked a lot like this, right? The only thing that's different is that beta is multiplying xn, and xn is another vector of values. But here we're making it multiply just 1. We insisted on it being 1. Where's the answer? Oh, geez. Animated, blah, blah, blah. There's that. And we wrote down this. Oh, we didn't. Where's the solution? Oh, here it is with SVD. Okay, we did it on the board. It's not in the slide, actually. All right. So I guess I'm not helping here by writing this. This isn't helping you. Okay, I will think in the next 5 minutes while you take a break about how to make this help you. I'm going to make this help you.
No matter what you say.
You give me. It's in the notes. It wasn't actually explicitly in the slides, but we did write it on the board. So here's the same regression problem. Minimize, except it's with different notation, right? This is y, vector y minus little p times vector x, but if you swap things around, it's the same problem. And we can write that as y minus px times y minus px. It's a dot product, right? The squared length, this is a squared vector length. We can write that as a dot product, or we can write it as the transpose of the vector times itself, right? That's a dot product. And when you solve this, you get this. You can differentiate this with respect to p and get this calculation, right? Solve for p, and you get this. The optimal p, in our case, it's going to be the thing that minimizes this. Let's just write it as this. It's this. X, it's the vector. You see, I have to translate the notation, but it's basically the product of the two vectors, the x and the 1 here, the x and the y there, the dot product of those two things, divided by the dot product of the vector that's multiplied by the thing you're solving for. This is px, so it's x transpose x in the denominator. So here, it's the same thing, except here, the thing that c is multiplied by is 1, the vector 1, vector full of 1s. So this is 1 transpose times 1, and in the numerator, it's x transpose times 1. Okay, so what is, we can start with the denominator. What's 1 transpose times 1? This is a vector full of 1s. So this is the dot product of that vector with itself. What do I get? I get 1 times 1 for each entry, and I have n of those, and I add them up, so I get n, right? So in the denominator, this is n, because I get, right, it's the sum of all those pairwise products, and they're all just 1 times 1, so I get n. And in the numerator, what do I get? The elements of the 1 vector, which are all 1s, times the elements of the x vector. So I get all of the elements of the x vector, each 1 times 1, and I add them up. So it's the sum of the elements of the x vector, the sum of the xn's. I divide by n. That's the mean, or the sample mean, right? The average. It's the average of the elements of x. Okay? So the answer, the thing that minimizes this, if I ask what c can I put in here, by the way, this is like, visually, you should think of all those weights on the seesaw, and I'm asking where should I put the fulcrum, that's C. Where should I put that so that it balances? And the place where it's going to balance is this. I have to put it at the mean. The sum of the values divided by n. Okay? So, I mean, this is not a surprising formula. You all know how to calculate an average. There it is. It's just sort of, we're deriving it as the answer to this optimization problem. Rather than just stating that's what we want to compute, we're saying, actually, that's the thing that minimizes the squared distances. Okay. So now, laptop is going to sleep. It can do that, you cannot. And there's the solution from the notes.
Yes, I
Yo. Okay. So, back to our question, why do we compute averages? Why is that a good way to summarize the data? So one answer is just, well, it's the solution to an optimization problem, this optimization problem, which is easy to solve. And as you all know, because we've been through it, I will remind you in a moment, it generalizes to multiple dimensions really nicely. So not only can we solve this optimization problem in one dimension, with data scattered along a seesaw, if I had a splatter of data in a two-dimensional space, I can also solve this optimization problem. You now think of it as, I have a weightless plate, and I have little data points, masses, sitting around on that plate, splattered however they were measured. I'm making two measurements for each. Each of these points is two measurements, an x and a y coordinate. And now I'm asking, how do I move the fulcrum underneath the plate so that it balances? Now it's a two-dimensional balancing problem, right? I have a plate, and I have to find out how to balance that. And the answer to that problem is really the same. It's still an optimization problem, and it'll still be, the answer is the mean. We sometimes call it the centroid when you go to multiple dimensions, because it's like the center of mass. It's the same thing as the mean. It's just another way of phrasing it, and it reminds you of this picture of balancing and masses. Okay? So it generalizes to multiple dimensions. It's the solution to this optimization problem. It generalizes to multiple dimensions. And one other thing, the computation of the mean is, if I want to compute some function of my data to give me the central tendency, this function is really simple. In fact, this function is what we say for functions that look like a weighted sum. It's linear, right? If I were to go make my measurements again and they all came out double, then what would happen to the mean? It would be double. If I take one set of measurements and I take somebody else's measurements, I take the mean of my measurements, I take the mean of their measurements, then I can kind of combine these two things. They add together. They're going to have to add together in a weighted fashion, because each one is a weighted sum of its inputs, 1 over n. The n's might be different. But the mean of the entire data set, all things combined, is just the weighted sum of the means of the two individual data sets. So it's linear. The mean is a linear calculation. And so we like linear calculations. They generalize to multiple dimensions. They're easy to describe. They're easy to compute. We know how to manipulate them. We know what happens to them. Like, what if I change the units? I make my measurements in centimeters, but it turns out that somebody else wants them in inches. Do I have to go back and convert all my data points into inches and then recompute the mean? Do I? No. You all know intuitively that you don't have to do that. What do? You just convert the mean from centimeters to inches. So why didn't I have to go back to all the data points and convert each one of those and then recompute the mean? You do it all the time. If I told you to do this, you would do it, right? You wouldn't go back. You wouldn't convert all the data into inches. You would just convert the mean. If you already had the mean in centimeters, you would just convert the mean and you would hand that over. How do you know you can do that? It's linear. You already knew how to exploit linearity. It's just a scale factor. So in a linear calculation, which this is, if I rescale all the data by some scale factor, multiplied by 3.8, actually 2.2 in this case, because I'm going from, or divide by 2.2 because I'm going from centimeters to inches, I can do that to each of the data points, but I could also just factor it out and just do it to the mean itself. I could just do it to the, I don't have to do it to all the data points. Saves me a huge amount of computation. If this is 10,000 data points, I don't have to do 10,000 divisions. I can just do one, assuming I've already got the mean in the original coordinate system under the original units, right? So that's pretty good. The mean is linear, and that means it's really easy to work with. It's easy to manipulate. It's easy to rescale. It's easy to switch to new units. It's easy to combine means from different measurements. It's easy to partition it, right, into pieces. It's just, we know how to work with it. So averages are good. And minimizing the squared error, which the average is the answer to, it's the thing that minimizes the squared error, becomes the optimization point, kind of the optimization problem, working backwards, that leads to this solution. Okay, so we have this whole package of things that fit together. Minimizing squared error, which is like the regression idea, using the mean, using things that are linear, all of this fits together. Okay. We've already seen all of that. I'm just kind of reminding you of it, and I'm kind of now saying it in terms of statistics. It's now about summarizing data that have noise in them or variability. Okay, but the mean wasn't the only choice, and in fact, there's a whole family of there are many choices we can write down. In fact, you can write down any measure you want of distance, and you can ask, how would I minimize that? And distance, distances should be positive, and they should be. There's actually technical rules. I don't want to get too mathy here because it's not necessary. I want you to understand the concept. A distance measure, to be a proper distance measure between two values, should have the following properties. It should be positive. It should be symmetric. If you swap the order of the two values, you should get the same distance. The distance between x and y should be the same as the distance between y and x. Swap the order. And it should be equal to 0 when the two things are equal to each other. Right? The distance between a thing and itself should be 0. And if it satisfies all three of those, there's one more, but we'll leave out the technical considerations, then it's a distance measure. Okay, so if you have so you can use any distance measure you want. If you can just make one up, write it down, and then say, I'm going to optimize that. And that's the way I want to describe my central tendency. And here's a whole set of them. These are called LP norms. Okay, so don't worry about the phrase or the technicalities. Just look at the idea. The idea is very simple. Instead of squaring this, what if I raise it to some different power? I decide I don't want to do 2. I'm going to raise it to some power p. Typically, when we write an LP norm, we also take the pth root at the end. So we take all the differences between the x's and some value c, we raise them to the pth power, and at the very end we take 1 over n of that, we add all of those up, and then we take the pth root. So this is kind of like if p was 2, then it's the same as this, except that we took the square root at the end. In other words, instead of minimizing the vector length of this thing, the squared vector length, you actually minimize the vector length. You take the square root at the end, so you don't have the square at the end. Okay? And the answer to that problem would be the same, because taking the square root at the end doesn't change where the minimum is, right? When I'm solving an optimization problem, if I take the thing that I'm optimizing and I apply some nonlinear function to it, and the nonlinear function is monotonic, that is, it's always sloped upward, it never can go down, then it preserves the order of things. The big things remain big, and the biggest thing, will remain the biggest thing, and the smallest thing will remain the smallest thing. So if I'm trying to minimize this, the thing that's smallest in this problem will be the same as the thing that's smallest if I were to take the square root of this, or if I were to take a log of this, or if I were to take the fourth root of this. I can put it through any function I want as long as it's monotonic, and it doesn't change where the minimum is. It will change the value of the minimum, but if I'm asking for the argmin, that is the position, where is the fulcrum, where does C have to go, the answer will be the same. It doesn't matter if I take the square root or not. So this 1 over p at the end doesn't really change the problem. What really matters is the p in here. And that will change the problem. So let's just look at some examples, because I think it helps to see that all those things that you already listed for me, remember I said mean. We landed on mean first, but it was the next thing that you listed, median. And then mode. Those are 3 examples, and those 3 examples actually come out of different choices of p. So there's actually, and there's other examples, not just those 3. There's a whole bunch of things that you can come up with to summarize the central tendency and the width of the data. Okay? So it turns out that if you set p equal 1, so now we're just going to take the absolute value of the x's minus c, and you try to minimize that, the answer is the median. And we can, if we want to use notation, we can call that m of x. So instead of mu of x, this is the mean of the vector x. This is the median of the vector x, m of x. And why is that? Why does that come out that way? Anybody see why that would be true? Maybe we can draw up like a quick picture to see it. So here's 1, 2, 3, 4, 5, 6. I need 7. Let's do 7 values. And what does this function look like if I set p equal to 1, right? I'm going to have to add up. So if I pick a c, let's just look at what happens if I pick a c. So I pick a c here, let's say. And the function I'm trying to minimize is to take each data point and measure how far away is it from c, and take the absolute value of that, and then add them up. Okay? So the function that I'm computing looks like this, right? This is an absolute value function, right? It says this is the absolute value of the distance away from c. So this function, if I'm sitting right at c, it's 0. If I move to the right, it grows linearly. It actually grows like a ramp as I get further and further away from c. So this point gets a big value. And this point gets a medium value. These points get really big values. Right? And then this point gets this value, and this point gets this value, and I add those up. And this one is, let's say, right at the bottom, so that gets a 0. And what happens? So that's the picture of what I'm computing. And now what I want to do is, I don't want it for any particular c. I want to find the best c. What's the c that minimizes this sum of values? So what happens as I move c? In particular, we can sort of take a derivative of this, right? So if I have the absolute value of the xn's minus c, just that with no squaring, and I'm summing this up, and I take a derivative with respect to c, what do I get? Well, if the absolute value wasn't there, what would happen if you take a derivative with respect to c? You get minus 1, and there are actually n of these, because this is a sum over n of these. So you would get minus n. If we divide by n, then you'd get minus 1. Okay? But that's not quite right, because the absolute value is there. So in fact, what you get equals, you get a sum over things that are, how do I write this? I get values that are minus 1 if x is bigger than c, and I get a plus 1 if xn is smaller than c. How do I know? Well, just look at the function. I drew it up here, right? What's the slope of this function? It's 1 here, it's minus 1 here. So basically, when I add these up, and I take the derivative of this, I'm basically going to evaluate this function at each of these data points, and I'm going to get plus 1s and minus 1s depending on which side they are of the bottom, right? And as I slide c along, what's going to happen? I'm going to convert plus 1s to minus 1s, or vice versa, right? The slope is going to change by integer amounts. Okay? This is not the value of the thing I'm minimizing. This is the derivative, right? So what's going to happen as I slide c along is that the derivative is going to jump suddenly. As I pass each point, it's going to flip from being something that's adding a plus 1 to the derivative to being something that's adding a minus 1 to the derivative. So I'm going to start off with, when I'm way, way out here, let's put c over here, my derivative is, the value of the function will be very large because all these things are going to add up. And the derivative is actually going to be negative. I think I have this backwards. It's actually negative 1 for xn less than c, and it's plus 1 for xn is greater than c. Does that sound right? Nope, I had it right the first time. Greater than, and this is less than. So, if I'm over here, and c is here, okay? This thing has a big value, and if I move c to the right, it's going to go down. That's kind of obvious, because all the points are to my right, and they have these big values. They're way up on this function, right? And if I move c a little bit this way, it's going to go down. So it's going to go down, 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 until I get to the first point. As soon as I pass the first point, the derivative is going to flip. This point will now flip from being on my right to being on my left. And now it's going to go into the plus column. So now my derivative is a little less than it was before. It's gone down by 1 increment, but it's still negative because most of the points are on my right. And as I pass each point, my derivative is going to drop by 1 increment. Down, down, down. And when will I reach the minimum? So similarly, let's try the opposite side. If I move c all the way over here in the middle of the slide, now it's an absolute value, right? Everything is on that side of the leg. And now the derivative is all negative. So that says if I want to decrease this, I should go this way, right? So I'm going to go this way. And I have these two things coming in together. Each one of them I'm getting better and better and better. I'm like reducing the total of this thing. And as I tick past each of these things, the derivative is going 1 notch less, less, less. And where do I get to the point where the derivative is 0? Well, it's when I have the minus 1s and the plus 1s balanced, right? When they cancel each other. Right? If I have an equal number, I'm always going to have minus 1s and plus 1s. And when I have an equal number of them, minus 1s and plus 1s, aha. Now the derivative is 0 because I add a bunch of 1s and a bunch of minus 1s, okay? And so if I want to set the derivative equal to 0, calculus-wise, to find the minimum of this thing, I have to find a place where the minus 1s and plus 1s balance, so I have to be in the middle of the points. I want an equal number of points to my right and my left. The ones on this side are the plus 1s, the ones on this side are the minus 1s, they cancel, and I have a derivative of 0. So that's the best I'm going to do. So I want to put c in the middle with an equal number of points on either side. If there are an odd number of points, as is drawn on the board, 1, 2, 3, 4, 5, 6, 7, where's the answer? It's the 4th point, right? This will be the best one. Because if I can put this absolute value right here, this c is right here, this point minus c is 0, this point minus c is whatever that distance is, and this point and this point, and if I take the derivative, I get 1, 2, 3, 3 plus 1s, and 1, 2, 3, 3 minus 1s, and they cancel. So the derivative is 0, and I'm not going to do better than that. If I move a little bit to the right or a little bit to the left, then this guy, the one that was right at C, is suddenly going to switch into the +1 or the -1 column, and it's going to throw me off. So I really want to be right on this middle one. That's the median, the middle data point. Okay, and there's one little trick. What if I didn't have an odd number of data points? What if I had an even number? Now what's the answer? I mean, people often choose something here, but it turns out that there's not a unique answer, right? Because where do I have to go to set the derivative equal to 0? Right. Anywhere between, well, it's kind of the middle 2 points, right? Because now there's 2 points. There's not 1 point in the middle. This is the 3rd point, and that's the 4th point. And if I'm anywhere in here, I have an equal number of points to my right and left, so my pluses and -1s cancel. And those are all equally good. In fact, the function looks like, it's like a blunted version of the absolute value, right? So the minimum value for this function is going to be in this range, and it will be the same throughout this range. If I go past this point, now it starts to grow, because I've just taken this point from the plus column and put it in the minus column. So the total derivative will be more minuses than pluses, so it'll be negative, which means that I should really go this way, right? This is, now the derivative is negative, it's telling me I should go left. And if I'm over here, then I'm moving past this point, then I'll have too many in the plus column, and now I should go right, okay? So you can see that the right answer, if you have an odd number of points, is to pick the middle point. If you have an even number of points, you can actually pick anything in that interval. Typically, people pick the middle of that interval to break the tie, basically, the ambiguity. But the answer is the median. So when you set p equal to 1 in this expression, and you minimize it, you get the median. Okay. So now we have the mean is what we get by setting p equal to 2. The median is what we get by setting p equal to 1. Now here's something weird. If we kind of take the limit as p goes towards 0. So what happens if you let p get really large or p get really small? We can kind of think about those two cases. So what happens when you let p equal, actually it's easier to do this one, let p go to infinity. So let's think about that one first, and then we'll do the other one. As p gets large, and you take an LP norm. So I'm taking easiest thing is probably to do, let's just do it for 2 values. Okay? So I'm going to let p get large. So what I do is I take each of the values and I raise them to some large power. Let's say at 10. Right? So the 10th p to the 10th power is a very, very steep function. It's not a parabola, it's something that goes really, really rapidly. So if you're just a little bit away from the origin, you end up with something pretty huge, right? You go out to, so all these functions, let me just say that first. These things where you take the absolute value and you raise it to the pth power, at 0, they're all 0. At 1, they're all 1. And at -1, they're all 1. So these points are true of all of these functions. And what's different about these functions, let's do the squared one first. So here's the squared one. Say that's quadratic. P equals 2, right? And p equals 1, you know what that looks like. It's this. It's straight lines, right, going through those 2 points. What is p equals 4? It's a steeper function, right? It kind of looks like the quadratic one, but it goes up even faster, right? But it still goes through those 2 points that are equal to 1, right? So this thing is going to have to do that. going to go up even faster, right? It has to go through these 2 points, because 1 to the 4th power is 1, and minus 1 to the 4th power is 1. So it has to go through these 2 points. It has to go through this point, 0 to the 4th power is 0. So all of these are going to go through those 3 points, but at the 4th power it goes up much faster. This could even be, let's say, p equals 10. It goes really fast, okay? And what happens if I go the other way? I go for p equals, I don't know, the square root. What does a square root function look like? Well, that looks like this. I drew it a little too shallow. Remember, it's the square root of the absolute value. Okay? So that thing, this is p equals 1/2. Here's p equals 2. Here's p equals 1. Here's p equals 10. Okay, so we have a whole family of functions. They're all 0 here. They all go through 1. And then the question is just, well, what do they do? Do they accelerate or do they decelerate? And if I combine my data, making measurements using one of these functions, and I ask, well, how do I minimize that? I get different answers. So we already went through p equals 2 and p equals 1. Those are listed, the first 2. Let's do p. Let's let p get really large. Okay. So I have a bunch of values, and I raise them to some really high power. The one that's the biggest becomes extraordinarily large, like way larger than any of the others. And when I add them all together, that one kind of dominates the sum. And then I take the pth root, it kind of brings them back. In the end, what happens is the biggest one wins. Because this thing accelerates so rapidly when p gets large, that the one that's furthest out dominates the whole sum. It just wins. So when you compute the LP norm of a group of numbers, what you get back with p large is something that's like the maximum. The biggest thing wins. It just crushes everything else. So when p goes toward infinity, what you get is the largest number. And if you want to minimize, so that's what you get out of this calculation, if you want to minimize that by recentering your data, moving that fulcrum, you want to minimize the value of the largest number. And when I say largest, I mean largest like distance from 0, where these things are all symmetric, so large this way and large this way are the same. So if I have this pile of data, and I want to move around, and I want to minimize my distance to the largest one, where large means in either direction, the best place for me to be is to kind of center myself so that I can just reach out and touch the 2 largest ones, and they're the same distance from me, from the center. So I want to take the largest and the smallest, if you like, the largest in both directions, and I want to take the midpoint of those 2. That's very different than finding the mean or finding the median. You don't find the middle one. You find the outliers, the 2 farthest away, and then you pick the point that's halfway in between. But that is a summary of the data, right? That's a summary of the central tendency. You've captured or described what your data look like by saying, find the biggest and the smallest and take the midpoint. So p goes to infinity, a large but really large p will give you the midpoint of the range. That's your summary of the data. Now let's do the opposite. So we have p equals 2, we have p equals 1. If we let p get really large, we take the midpoint of the range. If we let p get really small, what happens? So this is, let p go towards 0. Let it be tiny. So the square root is in that direction, right? I want to do something that looks like a square root. And if I do something like the 10th root, what does that look like? It looks like it's even sharper, right? It goes up really fast, and then it's almost flat. Here's the 10th root. What's it doing? This is p equals 1/10. So I take all my numbers, my distance from c, I take the 10th root. It kind of makes them all equal to 1. Or it like flattens it out so that they all look the same. Unless they're at 0. Because 0 still goes to 0. So the 10th root of 0 is 0, but the 10th root of everything else is like the same. So when I add all of these up, then I take the average, and I use the 10th power to put them back. That's the 1 over p that comes at the end, right? What's going to happen is I'm going to get a number which is basically just, every data point will count the same. Wherever they are, they're all going to count the same. So I'm basically adding them all up. I'm counting how many of them there are out here, except this one's not going to count. Anything that's right around 0 doesn't count. So I'm saying count all the things that are not 0. Count all the things that are not 0 and then give me that number. So when p is small, you basically count the number of non-zeros. So how do you minimize that? I want to move C. I have my data, my distribution of data. I want to move C around until I minimize the number, not of non-zeros, but of non-Cs. Right? I'm going to put C somewhere, because I want to put C in a place that minimizes this. I want to put it where a lot of data points fall on C, because then they won't count. They're sitting here in this notch. And everything else counts equally. So I don't really care where C is, except I want it to be in a place where there's a lot of data. And that's the mode. Find the place where there's the most data, the peak. If the peak happens to be like way off on the side, if I have a distribution, let's say my histogram, or let's not do histograms, let's do discrete data points. I have a ton of data over here on the left, and I have a few here, and then I have a few over here. These answers are all very different, right? The mode is here. It's this guy. Even though that's the leftmost point, that's the mode. That's the one that has the most data. So that's what you pick if you let p get really small. If p is infinity, or goes toward infinity, what do you pick? You take the average between the rightmost and leftmost point. It's like here. If you wanted to compute the mean of this, where would you end up? Well, that's the balance on the seesaw, right? You'd be probably like here. This is the 1,200-pound person, and this is the infant way out on the other end of the seesaw. To balance this, you got to put the thing right there. Okay, so the mean is really close to the mode in this case. And where's the median? Well, it's going to be, I don't know where it's going to be. It might be right at the mode. Depends how many numbers there are in each of these, right? Okay, so you see, these answers are all different. And of course, these are just examples. P equals 1, P equals 2, let P go toward 0, let P go toward infinity. You can pick P to be whatever you want. You can decide, I like 8. 8 is good. I'm going to let P equal 8. P equal 8, how will it behave? It's kind of like finding this midpoint of the range, but it won't be exactly. It's somewhere in between that and choosing the mean, which is P equal 2. So the behaviors can vary continuously. By the way, P doesn't have to be an integer. You can make it 8.3. You can make it 12.653. You can do whatever you want. Any P you want will give you a slightly different answer. But generally, the ones that we know about are the 4 that I gave you. P equals 2 gives you the mean. P equals 1 gives you the median. P equals 0, or P approaching 0 gives you the mode. And P approaching infinity gives you the midpoint of the range. So those are 4, if you like, standard things to do. And then there's a continuum of other possibilities by just adjusting P to be whatever you want. The thing to notice is that for each of these choices of central tendency, there is an associated choice for measuring the width, the dispersion. So if we do the P equals 2, the central tendency is the mean, and the dispersion is the standard deviation. They go together. It's not arbitrary that we end up using those two things together. They go together because one of them minimizes the other. The mean is the thing that minimizes the standard deviation, or the variance. When you use the median, you shouldn't report the standard deviation. It kind of doesn't make any sense, by the way people do it all the time. There's a lot of papers, you can go find papers all the time. They report, here's the median and here's the standard deviation. It actually doesn't make sense. The thing that you should be reporting with the median is the sum of absolute differences. It's a horrible phrase. It's basically the sum of the absolute values, i.e. you should compute with P equals 1, because the median is the thing that minimized that. So you minimize that, you express the position that minimizes that, and then you express the width around that, and you use the same measure to express the
What
width.
is a name for that?
What's the correct name?
The mean deviation.
Mean deviation.
Horrible word. but-
Which is also confusing as hell because it has the word mean in it. Right? So you see that the field was pretty confused. There's a right way to think about these, and it actually is very natural, right? These things come in pairs. And their solutions, these things, are solutions to optimization problems that involve these things, right? So I write down a measure of distance, that's this thing. And then for the measure of distance that I've chosen, there's a thing that minimizes the dispersion around that position, and I call that the central tendency. And then I have a pair of things to describe my data. There's to summarize my data. There's the central tendency is whatever I minimized, and then the spread around that is whatever the value of this thing is. The argmin is the central tendency, and the min, the value of the min, is the width. Okay. So, and you can, I don't need to say that much about these, but you can see that these measures have different advantages and disadvantages. I already kind of illustrated that with this very asymmetric example. So I have some distribution that's very peaked over here on the left side and spills out with a very, very occasional examples way out here. It's depending on what you want, these things are going to behave very differently. They're going to give you very different answers. The mean, the midpoint of the range, the mode, the median. They're going to give you different answers. You can also, another case that comes up where you get really different answers, and people often point to this case as a good example, is let's imagine I have data that happen to fall into two clumps. So I have some data points over here, and I have another set of data points over here, but I never end up with anything in the middle, okay? And what are these different values going to do in terms of summarizing the data? So already there's something weird about summarizing this kind of data with a central tendency and a dispersion. Because there's like two central tendencies, is sort of the intuition. Like you really don't want to describe this as a single thing with a single central tendency and a dispersion. If you compute something like the mean, or the midpoint of the range, or even the median, you probably, so if you compute the mean, what do you get? Let's imagine there's kind of an equal clump of data here and here. Your mean is here. Now that's a pretty weird thing to use to summarize the data, because that's in a place that never happens. Like that's a bad summary of the data, because there's no data point that looks even remotely like that. They either look like that or they look like that. They don't look like this. So this is kind of a bad summary in a sense. And you might say, okay, I'll pick the, it would be even worse if I let p get larger. So p equals 2 gives me the mean, that would put me here. If I pick p equals infinity, the midpoint of the range, that's like not going to help me, because the midpoint of the range, the maximum and minimum are here and here, so again, the midpoint of the range will be somewhere in the middle. If I pick the median, and I happen to have an odd number of data points, I might end up with like this one or this one. That, you could maybe say that's better, because at least it's close to a clump of data. If I pick the mode, I'm going to end up, well, in the way I've drawn this, I'll end up picking this. The mode's over here. It's this one that's where I happen to get a bunch of data points at this location, right? So now the mode will be here. So you can see that in a case like this, which is bimodal, two modes, that these measures or summaries are kind of not going to work that well, and maybe the best you can hope for would be to use something like the mode, which will at least pop one of these out and not give you something in the middle that doesn't actually explain anything. Okay, we'll encounter that again, but I just wanted to show it to you here. Okay, so these are the things. So the standard deviation is just the thing that we already wrote. It's the variance, and then you put a square root at the end, sample standard deviation. Looks like this. The mean absolute deviation. So this is what happens if you take the sum of the absolute values of the differences between the data points and the median, and that's appropriate. if you're using the median, if you want to use your median for central tendency, then you want to report this thing as your measure of dispersion, because the median is it minimizes this, right? The median is the thing that minimizes this expression. So these again, those two go together. There's one other thing, and all of these things are called descriptive statistics, and the standard ones are just about expressing the central tendency and the dispersion. There's another thing that often happens. People express quantiles, and I think you all know what quantiles are. You probably learned about those in high school or something, when you saw the beginnings of statistics. So quantiles are just basically carve up your data into equal numbers of data points, and the positions of those boundaries, like let's say I carve my data into 4 chunks. So there's quantiles that correspond to the first 25% of the data, the next 25%, the next, and the next. There's 4 chunks. And I can say, where are those boundaries for those quantiles? And that gives me some description, a little bit maybe more detailed description of how the data are laid out. That's another way of summarizing data using quantiles, and that shows up a lot. We're going to see how to generalize quantiles, but this is an idea that you've probably seen many times. You see it, when you read the newspaper, you hear about quantiles. Okay. So these are all measures, and they all are easy to describe, and they are used to describe data. What happens in multiple dimensions? So I have now, let's do 2 dimensions. So here's the data points. These are measured. And now they have horizontal and vertical position. They're 2-dimensional data points. I have 2 measurements associated with each point. And now I think, well, gee, I still want to describe, again, central tendency, and I still want to describe dispersion. So how do I do that? Well, okay, so now it's a little more complicated. Central tendency is not going to be a number anymore. It's going to be like a position. So the obvious thing, right? So this red dot maybe is the central tendency, like it would be the mean centroid, right? So there's a natural way to generalize all of that I said in 1D into the 2D case. And the generalization is to compute the mean, the average of the data in 2 dimensions. And now what about the dispersion? You guys know enough because of everything we went through with least squares and regression and total least squares and PCA and all of those things. You know that once you're in more than 1 dimension, the description of the width or distribution, the shape of the data cloud, is not a number. How do we describe the shape of a data cloud? What's one way to describe the shape of a data cloud? Not with 1 number, but with a... Didn't you do this in homework? Didn't you do a whole bunch of calculations using these things? We didn't call them by their statistical names because we were kind of avoiding that until now. But what is it?
Ellipse.
Yeah, right, so the geometry is that it's an ellipse. That's what's drawn on the slide. And how do we mathematically define, what do we use to characterize or describe that ellipse mathematically? 1 number? No? Okay. Eigenvalues and eigenvectors? Yes. Even before that, they're the eigenvalues and eigenvectors of what?
Collide.
Ah, there we go. Okay.
Yeah.
It is?
Yeah.
I always do this. I'm standing here trying to get you guys to give me an answer, and you're all sitting there looking at the answer, daring each other to not say it. Fine. Okay. So we calculate in 2 dimensions. We would calculate the covariance, not the variance, the covariance. And that's not a number. That is, in 2 dimensions, it's how many numbers?
3.
Yeah, it's really 3. It seems like 4 because it's a matrix, and it's a square matrix, right? A 2 by 2 matrix, but it's symmetric. So there's only 3 free numbers in there. The other one is just copied, right? The matrix, the covariance matrix is always symmetric. So how many degrees of freedom does it have? In 2 dimensions, it's 2 by 2, but the upper left and bottom, lower left and upper right are the same, so it's really 3 numbers. There's the 2 diagonals and 1 of those off diagonals. What if it's a 3 by 3 covariance? How many degrees of freedom? Well, if it's 3 by 3, there are 9 entries in the matrix, okay? Because it's 3 times 3, right? But again, the things that are off the diagonal are copied. They're not really independent numbers. They're just copied from what's above the diagonal. So how many are there? There's the 3 on the diagonal, and how many off the diagonal? Should I draw this? So there's these 3, and then there's 1 here, and 1 here, and that's it, right? Because the ones that are, there's 3 more down here, but they're just copies of these 3. So it's 1, 2, 3, 4, 5, 6. There's 6. Ooh, so it's not like, so the formula for figuring this out is not take the total number of entries in the matrix in 2 dimensions, that would be 4, and subtract 1 in 2 dimensions, that would be correct. You just take 4 and subtract 1, you get 3. That's the number of degrees of freedom. Ah, but that didn't work here because this was a 3 by 3. There are 9 entries, and we got 6. We don't subtract 1, we subtract 3. 3 over here. So what's the general formula? How do you calculate this? Anybody remember or know how to figure that out? I have to add up. The answer is going to be, if this is n dimensions, I have to, so if it's 3, what do? I take 3 for this row, and then 2 for this row, and then 1 for this row. I have to add that up. If it's n dimensions, I have to take n for the first row, n minus 1 for the second row, n minus 2 for the third row, n minus 3 for the third row, next row, all the way down to 1. And I have to add those numbers. And that's how many entries there are on or above the diagonal. So in general, what is that for an n-dimensional matrix, an n by n? Right. It's n plus 1 times n over 2. That's how many degrees of freedom there are in a covariance matrix. So, why am I fussing with this? First of all, because you should know that formula. It's a pretty simple formula. And it's really just the answer to how do you add up. Write it down. It's you have to add up n minus little n, let's say, as little n goes from 0 up to capital N. Okay? This is the answer to that. And you can, I'm going to leave it to you if you want to puzzle through how to solve that. If I wrote it down this way, this is just the sum of the number of elements in each row, independent elements in each row, and it gives you that. Okay, so why does that matter? Because we're talking about summary statistics, right? We're trying to summarize the data. So how many numbers do I need to summarize the data? The answer is, in n dimensions, I need the mean, which is just a vector of n values. In 2D, the mean is just a 2 vector. It's the coordinates at that point, right? And I need the covariance, which is a matrix that has not n squared values. It's something that scales with n squared because there's 2 n's in it, but it's n plus 1 times n over 2, that many values. So the total number of things that I need to summarize the data are n plus this. The mean plus the covariance. Okay. And why do we use, back to the same question, why do we use the mean and the variance? Why don't we use something else? I just gave you in 1D a whole family of things that we can use that are not mean and variance, right? You can use the median and the mean absolute differences. Or you can use the mode and the L0 norm. Or you can use the middle of the range and the L infinity norm. And all of those things are equally reasonable choices for how to summarize again, the central tendency and the dispersion. Why do we use the mean and the variance? Well, in multiple dimensions, it becomes more pressing. In 1D, we can calculate any of those things we want, but in multiple dimensions, it's actually not, first of all, it's not so obvious how to generalize all those other ones to multiple dimensions. Second of all, they're harder to compute. They're going to be harder to compute to sort of figure out those things. The mean and the covariance are easier to compute. The mean is a linear calculation, even in multiple dimensions. We know how it transforms. If we take the data and we reshape or we change our units, again, it's trivial. Now you have to calculate how does the mean change and how does the variance or covariance change. We know how to do that. So in fact, we fall back on these as the most standard descriptors of central tendency and dispersion because they're easy to compute, they're easy to work with, and they generalize really well to multiple dimensions. It's all basically back to linear algebra. And like all of statistics kind of rests on this. We use these things all the time as descriptions of data. Okay, so next time we will work through a little bit about partitioning of mean and variance, and then we'll kind of go back and kind of formulate things in terms of natural probability. We'll see if there's